Are they diabetic or not? And we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean is the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score. And finally, accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, Y test, Y predict. So those are the two values we're going to put in there. And let me go ahead and run that and print it out. And the way you interpret this is you have the Y predicted, which would be your title up here. We could do, let's just do PRED. Predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model.
So what is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what K-means clustering is all about. The term K is basically a number. So we need to tell the system how many clusters we need to perform. So if K is equal to 2, there will be 2 clusters. If K is equal to 3, it's 3 clusters, and so on and so forth. That's what the K stands for. And of course, there is a way of finding out what is the best or optimum value of K for a given data. We will look at that. So that is K-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player and the wickets taken by the player. And based on this information, we need to cluster this data into 2 clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data which consists of primarily 2 characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with k-means clustering, we will have here, that means k is equal to 2, and we will have two clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in k-means clustering is the allocation of two centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want 2 clusters, which means k is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. They are random points. They are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them 1 point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, so that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these two clusters. So we have this one initial cluster, this one initial cluster, but as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined and the original randomly allocated centroid is repositioned to the actual centroid of these new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation where the centroid doesn't need any more repositioning, and that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We will talk about the types of clustering, what is k-means clustering, application of k-means clustering. K-means clustering is done using distance measure, so we will talk about the common distance measures, and then we will talk about how k-means clustering works and go into the details of k-means clustering algorithm, and then we will end with a demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are primarily two categories of clustering: hierarchical clustering and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D and E, form one more. Then we combine D, E, and F, one more bigger cluster, and then add B, C to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is a top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes: k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together, but while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means objects can belong to more than one cluster. So that is the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially k-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now let's go and check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flowchart of the whole process. There is a starting point, and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with. And then as we progress, we keep changing until we get the best clusters. Or there is a technique called elbow technique, whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly, that to start with, randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is, for the new groups, for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point. And if required, the data points are reallocated to the new centroids, and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid, and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart, so let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop. So let's say we have a data set for a grocery shop, and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares. And the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters. And for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value. And that's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here, we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS because that pretty much gets stabilized. Okay, now that we have got the value of k, and let's assume that these are our delivery points, the next step is basically to assign two centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They've been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated. And the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated. Like so. You see this? So this point earlier was closer to C2 because C2 was here. But after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster. With this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. And then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups because we have assigned the value of k. So there are k centroids, and so there are k groups. All these inputs have been split into k groups. However, remember, we picked the centroids randomly, so they are not real centroids. So now what we have to do? We have to calculate the actual centroids for each of these groups, which is like the mean position. Which means that the position of the randomly selected centroids will now change, and they will be the mean positions of these newly formed K groups. And once that is done, we once again repeat this process of calculating the distance, right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3, and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to CK and find whichever is the lowest distance and assign x2 to that centroid, and so on. In this process, there may be some reassignment. X1 was probably assigned to cluster C2, and after doing this calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing. And that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick K cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to CK. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each X value from each C value. So the distance between x1, c1, distance between x1, c2, x1, c3, and then we find which is the lowest value, right? That's the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2, find the distance of x2 from c1, x2 from c2, x2 from c3, and so on up to ck, and then assign it to the point or to the centroid which has the lowest value, and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into K groups because we wanted to create K clusters, right? So we have K groups. Each one may be having a certain number of input values. They need not be equally distributed, by the way. Based on the distance, we will have K groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group, which means the original point which we thought was the centroid will shift to the new position, which is the actual centroid for each of these groups. Okay? And we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids. And if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have K groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids, and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of K-means clustering. We will actually see some live demos in Python Notebook using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida. and it wants to find the optimal store locations. Now the issue here is if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python notebook. So in this block, we are basically importing all the required libraries like NumPy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the points, data points, to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is, we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like Matplotlib and NumPy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead and, so we just mentioned 4. So it will go ahead and create some test data for us. And this is how it looks. As you can see, visually also we can figure out that there are 4 distinct classes or clusters in this data set. And that is what make blobs actually provides. Now, from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and we'll create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. This n underscore clusters is the value of k. Remember, k-means, in k-means, k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4. And so that instance is created. We take that instance, and as with any other machine learning functionality. Fit is what we use, the function, or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So X has these values, the data that has been created, right? So that is what we are passing here. And this will go ahead and create the clusters, and then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or I will actually start from 0, cluster 0, 1, 2, and 3 maybe, and then for each of the observations it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k means. When we call predict, that is what it does. And we can take a quick look at these y underscore k means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that. Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance, and you mention how many clusters you want by specifying this parameter n underscore clusters, and that is also the value of k, and then pass the data to get the values. Now, the next section of this code is the implementation of a k-means. Now, this is kind of a rough implementation of the k-means algorithm. So we will just walk you through. I will walk you through the code at each step, what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering, and there is a function or a library calculates for a given 2 pairs of points. It will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest. And accordingly, we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid, and then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare, and if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop, it only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but in the change will be very minor. So in that case, also that is actually convergence, right? So for example, the change is 0.0001. We can consider that as convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find underscore clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be 2 examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. As usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically, we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So this colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors, and this is the shape of this image, which is basically, what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically we have captured this information. So data is what, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1. And the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code, and this is the shape. So we now have also, what we have done is we changed using reshape, we converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. Right, so if you earlier noticed, in case of China the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this. And so this is how the original, the color, the pixel distribution is. These are two plots. One is red against green and another is red against blue, and this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that there are these. This is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very completely different or anything like that. Now we apply the newly created colors to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall the high level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the Summer Palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also 3-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python notebook. Alright, so let's apply the same technique for another picture, which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here, and we will also bring this. As you can see, the numbers are much big, so we will much bigger, so we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix, and we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors. And this is basically how it would look, 16 million colors. And now we can create the clusters out of this. The 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors. And then we go ahead and apply this and visualize how it is looking for with the new just the 16 color. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a slightly a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering, and we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering, and we use some sample data using blob to just execute the k-means clustering.
When we talk about the principal component analysis, we're going to cover dimensionality reduction, principal component analysis, what is it, important PCA terminologies, and you'll see it abbreviated normally as PCA, principal component analysis, PCA properties, PCA example, and then we'll pull up some Python code in our Jupyter Notebook and have some hands-on demo on the PCA and how it's used. Dimensionality reduction. Dimensionality reduction refers to the technique that reduces the number of input variables in a data set. And so you can see on the table on the right shows the orders made at an automobile parts retailer. The retailer sells different automobile parts from different companies. And you can see we have company BPAX, Isomax, and they have the item, the tire, the axle, an order ID, a price number, and a quantity. In order to predict the future sales, we find out that using correlation analysis that we just need 3 attributes. Therefore, we have reduced the number of attributes from 5 to 3. And clearly we don't really care about the part number. I don't think the part number would have an effect on how many tires are bought. And even the store, who's buying them, probably does not have an effect on that. In this case, that's what they've actually done, is remove those. And we just have the item, the tire, the price, and the quantity. One of the things you should be taking away from this is, in the scheme of things, we are in the descriptive phase. We're describing the data, and we're pre-processing the data. What can we do to clean it up? Why dimensionality reduction? Well, number one, less dimensions for a given data set means less computation or training time. That can be really important if you're trying a number of different models and you're rerunning them over and over again. And even if you have 7 gigabytes of data, that can start taking days to go through all those different models. So this is huge. This is probably the hugest part as far as reducing our data set. Redundancy is removed after removing similar entries from the data set. Again, pre-processing, some of our models, like a neural network, if you put in 2 of the same data, it might give them a higher weight than they would if it was just one. So we want to get rid of that redundancy. It also increases the processing time if you have multiple data coming in. Space required to store the data is reduced. So if we're committing this into a big data pool, we might not send the company that bought it. Why would we want to store 2 whole extra columns when we add it into that pool of data? Makes the data easy for plotting in 2D and 3D plots. This is my favorite part. Very important. You're in your shareholder meeting. You want to be able to give them a really good, clear, and simplified version. You want to reduce it down to something people can take in. It helps to find out the most significant features and skip the rest, which also comes in post-scribing. Leads to better human interpretation. That kind of goes with number 4, where it makes data easy for plotting. You have a better interpretation when we're looking at it. Principal component analysis. So what is it? Principal component analysis is a technique for reducing the dimensionality of data sets, increasing interpretability, but at the same time minimizing information loss. So we take some very complex data set with lots of variables, we run it through the PCA, we reduce the variables. We end up with a reduced variable setup. This is very confusing to look at because if you look at the end result, we have the different colors all lined up. So what we're going to take a look at is, let's say we have a picture here. Let's say you are asked to take a picture of some toddlers and you are deciding which angle would be the best to take the picture from. So if we come up here and we look at this, we say, okay, this is one angle. We get the back of a lot of heads, not many faces. So we'll do it from here. We might get the one person up front smiling. A lot of the people in the class are missing, so we have a huge amount off to the right of blank space. Maybe from up here, again, we have the back of someone's head. And it turns out that the best angle to click the picture from might be this bottom left angle. You look at it and you say, hey, that makes sense. It's a good configuration of all the people in the picture. Now, when we're talking about data, it's not, you really can't do it by what you think is going to be the best. We need to have some kind of mathematical formula so it's consistent and so it makes sense in the back end. One of the projects I worked on many years ago has something similar to the iris. And if you've ever done the iris data set, it's probably one of the most common ones out there where they have the flower and they're measuring the stamen in the petals, and they have width and they have length of the petal. Instead of putting through the width and the length of the petal, we could just as easily do the width to length ratio. We can divide the width by the length and you get a single number where you had 2. That's the kind of idea that's going on into this in pre-processing and looking at what we can do to bring the data down. The very simplified example on my iris petal example. When we look at the similarity in PCA, we find the best picture or projection of the data points. And so when we look down at from one angle, we've drawn a line down there, we can see these data points based on, in this case, just 2 variables. Now keep in mind, we're usually talking about 36, 40 variables. Almost all of your business models usually have about 26 to 27 different variables they're looking at. Same thing with like a bank loan model. We're talking 26 to 36 different variables they're looking at that are going in. So what we want to do is we want to find the best view. In this case, we're just looking at the XY. We look down at it and we have our second idea, PC2. And again, we're looking at the XY, this time from a different direction. Here, for our ease, we can consider that we get 2 principal components, namely PC1 and PC2. Comparing both the principal components, we find the data points are sufficiently spaced in PC1. So if you look at what we got here, we have PC1. You can see along the line how the data points are spaced versus the spacing in PC2. And that's what they're coming up with. What is going to give us the best look for these data points when we combine them? And we're looking at them from just a single angle. Whereas in PC2, they are less spaced, which makes the observation and further calculations much more difficult. Therefore, we accept the PC1 and not the PC2 as the data points are more spaced. Now, obviously, the back-end calculations are a little bit more complicated when we get into the math of how they decide what is more valuable. This gives you an idea, though, that when we're talking about this, we're talking about the perspective, which would help in understanding how PCA analysis works. What we want to go ahead and do is dive into the important terminologies under PCA. And important terminologies are views, the perspective through which data points are observed. And so you'll hear that if someone's talking about a PCA presentation and they're not taking the time to reduce it to something that the average person, shareholders, can understand, you might hear them refer to it as the different views. What view are we taking? Dimension, number of columns in a data set are called the dimensions of that data set. And we talked about, you'll hear features, dimensions. I was talking about features. There's usually, when you're running a business, you're talking 25, 26, 27.